Hello, this is Mr. Huber. In this lesson, we're going to continue to look at polynomials and their zeros, how those relate to the graphs, and also something else with the graphs, relative minimums and maximums. First, let's talk about the zeros. Remember that the zeros of a polynomial function, also sometimes called the solutions, are the x values where the value of the entire function, the y value for the f of x, would be 0. These are the x-intercepts. We can see those here. This point here, this point right here, and this point right here. Those are the zeros of this particular function. We can remember and see in factored form, x minus 2, that means x equals positive 2 would be one of the zeros. X plus 3 means negative 3 would be one of the zeros. And x minus 1 means positive 1 would be another one of the zeros. So our factored form for this, okay, relates to the zeros for that graph. If we see another example here, this brings up something a little different, where we see negative 7 is a 0, so that's why we have x plus 7 as one of our factors. And then when this graph is drawn and we come down and we hit the x-axis right here again at this point, at 5, it doesn't necessarily cross over the x-axis, but it has that turning point there. Okay, that's called a double root, okay, a double zero. So x minus 5, because 5 is the 0, x minus 5 would be one of the factors, and then since it's right at that turning point, it's x minus 5 squared. That's called a multiple root, okay? And we want to be aware of where we have multiple roots in our different equations. Okay? So let's look at what that could entail here. Another example, if we find the zeros of this function and state their multiplicity, okay? We're going to find the zeros and state the multiplicity of them, if there are any. So in this first example, relatively straightforward, the zeros are going to be negative 5, 2, and negative 1. Often we'd write those in order from least to greatest, but it doesn't matter. Those are the x values. They're the solutions or the zeros of that particular function. In this next example, we want to remember we want to write 5x plus 3 equals 0. And if I subtract 3 on both sides, I get 5x equals negative 3. And I divide by 5 on both sides, I'm going to get x equals negative 3 over 5. So be aware, remember up here, this would be like putting x plus 5 equals 0. Subtract 5 on both sides, we get x equals negative 5. That's why negative 5 is one of the solutions or the zeros or the roots of this particular function. Okay? Here, you might actually need to write that out. Up here, you can just look at this maybe and go, oh, I know negative 5 plus 5 is going to give me 0. Here, you might not be able to just look at this and recognize what goes in there for x to make that 0. So set the factor equal to 0 and solve it. And this other one now, x minus 4 equals 0 is going to be x equals 4. Okay? X equals 4 is another solution, and it's got a multiplicity of 2. Okay? It's a double root. Because of that squared here, that means this root is a double root. It's got a multiplicity of 2. So x equals 4 is a root twice. If this was x minus 4 to the third power, it would have a multiplicity of 3. So we want to be able to recognize where we have that. And again, remember what it looks like on a graph is where one of those turning points where the graph goes from here, it's going decreasing back to increasing, a turning point. Okay? If that turning point's right on the axis, that's called a double root. It could be a third, it could be a root with a multiplicity of 3, again, depending on the function in the equation. So we have 2 solutions, 2 roots, 2 zeros, remember all meaning the same thing, negative 3 over 5, and 4 has a multiplicity of 2. All right. When did the Winter Olympics start? They started after the Summer Games, which had been participated in for a few years first, and the Winter Olympics started in this way. There was actually plans to hold Winter Olympics, if you will, not to be called that yet, in 1916, but they were canceled because of World War I. So in 1924, France hosted the first International Winter Sports Week. Okay, it wasn't called the Olympics at the time, but they did this in advance of the Summer Games to help promote the Summer Olympics that were coming up later that year. And since then, every 4 years, they started hosting what became known as the Winter Olympics. So originally called International Winter Sports Week in 1924, and then thereafter known as what we know today as the Winter Olympics. All right. let's recall some other information here we know about something like minimums and maximums, okay? The minimum and maximum of a quadratic, which we've seen before, is that y value of the vertex, right? This point right here in this particular graph would be the minimum, right? That's the lowest value we could get for this parabola. So right there, that y equals -3, that would be the minimum value. We would say that this particular function or graph has a minimum of y equals -3. Right? And recall, we can find those points using our graphing technology, calculators, other programs, where we can set boundaries on either side of this. Right? We can go on our calculator, for instance, and we can set a boundary, left boundary, right boundary, as long as we're on either side of that point for our left and right boundary, and then it will calculate where that minimum or maximum is. So go back and make sure you're familiar with how to use that. We're going to see an example next of where you're going to be able to use the minimums and maximums in practice and see if you're kind of remembering how to do that in something that's not a parabola. Okay, so we're going to extend a little here. And we're going to talk about relative minimums and maximums. Okay, this graph doesn't have a maximum value because the whole graph goes up forever. It'll keep going up and up and up, and there's no end to the maximum this could be. Same with the minimum, it goes down forever. But this point right here is called a relative maximum, or sometimes a local maximum. It's the maximum value of the graph in this particular region of the graph. Okay? Over here in this particular portion or region of the graph, it has a minimum value. Okay? Even though the graph down here will go lower, this is a relative minimum. So we could look at this like it's part of the graph is part of a parabola, if you will. This part right here looks like a parabola opening down. So it has a maximum value at this point right here. Okay. And then we could look at this other portion of the graph, and it looks like a parabola opening up. And it has a minimum value there at the bottom of that particular portion of the graph. So we want to be able to calculate those relative maximums and minimums. And we're going to see what that looks like here. You can practice it and make sure you're familiar with how to do this on your graphing technology, where it's not going to be an exact value, but some decimals. You're not going to be able to just look at this graph and go, oh, I can see that that's a minimum of -3, like in that parabola that we had. Okay. So in this graph, this point right here would be a relative maximum, right? That's the maximum value for this portion of the graph. So when you go to calculate a maximum, you're going to calculate a maximum, and you're going to set a left bound and a right bound anywhere that's on the left of this point, and then right bound on the right of that point, and then you calculate, and your graph will give you the maximum for the area between your left and right boundary. So it'll give you the maximum right here, and this should come out, if you've done it correctly, this should come out right here, this point, to about 1.13. Again, we can round to a couple places, and 12.13. When you graph this, you may need to adjust your window. If you're in a standard window that only goes up to 10, and it cuts off here, you might not see this. You need to adjust your window and set your y values to go higher than 10 before you do that. Okay, so practice, make sure you're comfortable with how we can do this on whatever program or calculator you're going to use. Okay? And now down here is a relative minimum. Okay? A relative minimum down here, because this is the minimum value in this particular portion of the graph. So again, we're going to want to set a left and right boundary. Again, as long as they're anywhere on either side of this, left of this point, right of this point, a left and right boundary, and we're going to calculate that point right there. And when we do that, this point right here, this relative minimum, you should get 3.54 and -1.76. So this has a relative maximum, okay, at that first point we calculated, a relative maximum of y equals 12.13. Then it has a relative minimum of y equals -1.76. I don't know why I wrote a 5, 1.76. Okay. So we've got a relative maximum here. That's the highest point in this particular portion of the graph. We have a relative minimum, the low point in this particular portion of the graph. So relative maximum, relative minimum, and we can calculate those by finding maximums and minimums like we did with parabolas. So make sure you're comfortable with that process and how to do that.